first, they have longer penetration depths. So if you're using like microwave sensors, and they can better penetrate through the vegetation layers and even even enter the branch and trunk, more than just leaves in where chlorophylls, reflect and observe. Yeah, well, the chlorophylls are. So as compared to X-band or C-band, which has a shorter wavelengths, if you use L-band, you can enter deeper than the X-band or C-band even. Of course, more than the infrared sensors. So there are some variable named vegetation water contents, which is well incorporated into the L-band LMAP vegetation model. And this equation is pretty much show how we can simulate vegetation, brightness temperature to be measured by L-band microwave sensors, um, which consist of soil temperature and vegetation temperature and nadir vegetation opacity, something just beneath the sensor, and vegetation single scattering albedo and soil reflectivity. And important thing is that exactly like uh, equal stress vegetation energy balance model, this tau omega model also consists of soil part and vegetation part. And for the vegetation part, there they consider vegetation attenuation factor because they estimate soil beneath the vegetation layer. So they want to uh, subtract that emission from the vegetation. Um, Vegetation water content is well embedded into the small sense map soil moisture retrieval algorithms, which actually retrieve soil moisture from the minimization of cost function between uh, satellite observed brightness temperature and L-band vegetation model retrieved brightness temperature, and brightness temperature can be estimated from the equation here, which consists of soil temperature, vegetation temperature, nadir vegetation opacity, to be viewed from the bottom of the detector, and vegetation single scattering albedo, and rough soil refractivity. And the first term is explain the soil term. The other one represents canopy part. For its part, which considers extinction effect and something like a vegetation attenuation factor. The vegetation layer attenuates the soil contribution because we measure in this retrieval algorithm soil moisture beneath the vegetation layer. So there's some factor, attenuation factor from it. So that really depends on transmissibility, which is a function of VOD, vegetation optical depth, and vegetation optical depth expressed by VOD is again a function of vegetation water contents expressed by VWC. So this relationship VOD is equal to B multiplied by VWC is empirical relationship suggested by Jackson and Schlumberger in 1991, and B is vegetation coefficient depends on a type of vegetation. So for the crop case, it's 0.12. So the bottom line is that we really need to consider the vegetation attenuation factor, and for this we have to estimate vegetation water contents. And so as long as we can determine vegetation optical depths, we can also estimate vegetation water contents. There's some technical advancement from traditional soil moisture retrieval algorithm. Previously, people estimated and retrieved soil moisture from that cost function that we just explained. Minimize the cost differences between brightness temperature model and breath temperature observation. But nowadays, people start to retrieve soil moisture as well as vegetation optical depths simultaneously together from the cost minimizations. So those are measured on multi angles, and so previously vegetation optical depths was expressed as the function of NDVI or LAI to estimate VOD, but now they don't rely on optical indices any longer, so that you can estimate a vegetation property without being affected by their uncertainties and errors, and that the traditional issue that vegetation index only consider the chlorophyll contents rather than the moisture. And if you are using L-band microwave sensors, and then they can enter dense vegetation better than C-band or X-band, which has a shorter wavelengths. And also, as compared to active microwave sensors like SAR, some other type of radar, passive sensor is much less sensitive to vegetation structure. And topography. In case of using, when you're using radar, people actually prefer SAR because of such a high resolution. However, we really have to consider that it's not really easy to retrieve or isolate soil moisture information from SAR, because there are some more complicated factors that affect scatter coefficient more sensitive than the soil moisture. Yeah, so this is obviously very good advantages of passive microwave sensors. However, when you actually look at vegetation water contents, and I have plotted that over fire events, they did not really retrieve any spikes. Like, for example, yeah, so we were going to see some other comparison data later on this session. However, there was some fire event on several days, 208 and 212, 212, 213, 215, and so on. There were several fire events, but vegetation water contents, SMAP vegetation water content did not show any peak, because traditionally they used NDVI climatology, years of climatology of NDVI to estimate a vegetation water contents, and perhaps that's why there's no fire dynamics at all. So we also looked at vegetation optical depths after updating their retrieval algorithms and simultaneously retrieving soil moisture and optical depths together rather than relying on vegetation index. However, they did not really properly show the fire dynamics. If you look at in here, left hand side, left. right. Um, This is the vegetation optical depths, which has to be linearly correlated with vegetation water contents that we have seen in the Jackson and Schlumberger equation. However, even after the fire events on the date of 208 or 212 or 215 or date of year 220, there were we couldn't find any correlation with the fire events very well. Even for the soil moisture, if you can see the right hand side, by theory, soil moisture should be correlated with fire events. However, there were several issues with retriever algorithms. So because of vegetations and some other input data and some another issue is that the retrieval algorithm used for SMAP and SMOS, they use tau and omega model, which is actually optimized for crop mid-level crops rather than forest. So when we apply the soil moisture product over forest area, there is actually higher uncertainty in their accuracy. Anyway, if you look at the right hand side, we expected a low soil moisture before the fire event so that we can make some predictions before the combustion and flaming. However, we could see that soil moisture has been decreased after the fire event, but it's shown it's still wet before the fire event, as you can see in the line on the day of year 212. There were wildfire ignition. However, before this ignition, soil moisture were relatively moderately wet. So this is actually different from our expectations. Yeah. So, by theory, vegetation optical depths and soil moisture should be nicely correlated and must have some predictability before the combustion and wildfire. However, there were several issues, some technical issues and retrieval procedure, so it's not the always case, and we have to be very careful about the data interpretations. If you look at VOD, this is the another study that has been conducted for something like relatively smaller scale, and these were large scale. These were large scale. These were Canadian wildfires in 2018. 2018 BC Canadian wildfires. These are very large, like million hectare scale wildfires. 2018, and this is also 2018 Canadian wildfires. However, this is a small scale wildfire, and they found that vegetation optical depth is kind of better correlated with leaf water potentials, much better than the LAI. When they use it, passive microwave vegetation optical depths. So it really depends. Yeah, depends on the scale and your area and type of vegetation and so on. The other options that we'll like to introduce for the estimation of fuel condition is actually vegetation temperature. So in case of wildfires, it would be forest temperature. Steph Hessen addressed about the need of vegetation temperature in their study here, that ecology research heavily relies on the coarse gridded climate data based on standardized temperature measurements recorded at 2 meter high. in open landscapes. However, many organisms and experience environmental conditions that differ substantially from those captured by these macroclimatic free air temperature grids. In forests, the tree canopy functions as a thermal insulator and buffers subcanopy microclimatic conditions, thereby affecting biological and ecological processes. To improve assessment of climatic conditions and climate change related impacts on the forest floor diversity and functioning, temperature grids reflecting forest microclimates are thus urgently needed. Um, so if you see the figure here, air temperature is somewhere up here. Yeah, somewhere up here. Whether temperature is yeah, here. So weather station, they usually measure air temperature up here. However, when we say like crop temperature or forest temperature is something that inside this vegetation, so that's actually there's a large temperature gradient, and we really need to estimate this forests and canopy temperature to understand fuel conditions rather than meteorological conditions. Right now, like we just briefly discussed in the previous slides, in the most of models, when uh, in the most of models, when energy balance is calculated to estimate land surface temperature, they assume that land surface temperature has no heat capacity. However, this is not the case, and usually tree heat capacity increases with vegetation moisture content, so this is another source for the errors and uncertainty. As we often discussed in this session and previous session, when you're using Moody's thermal land surface temperature, although surface temperature is highly affected by hydrological factors such as like precipitation and snow cover, this is not considered for forest emissivity and Moody's land surface temperature retriever. Instead, they are linearly approximated as a function of vegetation index. So it's there's likely that there's something like uncertainty in their final products. So that's the need to retrieve vegetation temperature. And we actually looked at this element vegetation model, tau omega model, in previous slide when explaining about vegetation water contents. They assume that canopy temperature is equal to soil temperature and air temperature in retrieving their retrieval algorithm. However, yeah, we already discussed it that that's not valid assumption for heat wave conditions under warming environment. So that can be another source for uncertainty in their soil moisture retrieving algorithm. And we also visited two source energy balance model when looking at the eco-stress evapotranspiration. They actually approximate radiometric temperature with with the measurement of eco-stress land surface temperature. However, we can actually estimate it from microwave sensors. Of going back a little bit. Yeah, so the same two source energy balance equation can be applied to microwave sensors. Instead, in this equation here, um, Yeah. As you can see here in box, in case of eco-stress algorithm, they approximated radiometric temperature side as eco-stress on surface. However, this can be estimated from the microwave sensors. So this T sub R radiometric temperature is the same one up here in here in this box. Yeah. So they assume that radiometric temperature is to be the EcoStrat LST, and here you are able to estimate it with L-band microwave brightness temperature. You can plug in brightness temperature in here, and emissivity is brightness temperature, and can be estimated from brightness temperature, microwave sensor, and then from microwave sensors and surface temperature. And then you can estimate microwave as observed radiometric temperature, and from radiometric temperature you can estimate canopy temperature. So it's basically using the same type of two source energy balance model, but that consists of a soil part and canopy part. But we estimate radiometric temperature from microwave sensors with different power in Stepan-Boltzmann equation, which will be calculated for the L-band. If doing it, and then we can see that unlike the vegetation water content, the SMAP vegetation water content is over the same year and fire areas, there was a nice fire dynamics consists of three phases: incipient, before the ignition, and the flashover stage at the combustion stage, and the decay until extinction. We have seen the vegetation development figures up here. Here, yeah, this one, yeah. This one has been nicely expressed in this figure here. So canopy temperature nicely and gradually increasing, yeah, as the fire enters the combustion and flashover stage. And so when they consume all of the heat energies, as they store the heat during preheating stages, and then they enter decay and release all the fire energy that they stored. So we applied it to a different year, and the pattern was similar. They store a lot of heat at preheating, pre-ignition stage, and then they reach a combustion, and after releasing all the heat energies, and then finally they enter the decay phase and finally reach the extinction. We also applied a similar thing to different areas, and it was very similar. It showed very similar evolutions. If you compare canopy temperature, pre-fire canopy temperature with the lightning and the fire burned area, on the right hand side in B and D, pre-fire canopy temperature, well, nicely related to fire burned area. So as the temperature gradient within several days for how long it was? for 10 days. When there's a consistent increase of temperature for 10 days, those temperature gradient were nicely related with fire burned area. So pre-fire, before the combustion or flaming, if you are closely monitoring forest temperature, that can be a good indicator of fire spread and prediction of fire spread. On the right hand side, we also compared it with lightning density. We found out that there were as the contribution of lightning is more like a local rather than fire spread. So although there were higher lightning density, that did not really contribute to um, burned area size. Yeah, did not really positively correlated to that. So instead of lightning, pre-fire forest temperature seems to be a more direct contributor to fire burned area. This is just spatial distribution of canopy temperature. You can see that over a fire area shown by red contour is pretty much experienced elevation of canopy forest temperature before the fire occurrence. And blue dot is blue dot represent lightning, and the pink triangle represent ignition location. So if you closely look at it, although there even in figure C, in figure C here, there were several lightning around here, but only there was ignition up here. And even in here, there were several lightning around here, but there were no fire occurrence. And here, yes, there were several lightning over here, and yes, fire occurred around there. Here, yes, there were several lightning, and then fire occurred in the lightning dense area. However, yeah, sometimes that's yes, but other times there were no fire occurrence over the lightning area. So that's really depends on the case. We really have to closely look at what caused this large scale wildfires. So according to statistics, lightning is only correspond to 50% of fire occurrence. This is just for comparison. A shows the canopy temperature. B is Moody's active fire, and C is fire weather index. D is Moody's fire radiative power. So most of warm forest area, with a higher forest temperature, actually experienced fire occurrence. And the number B, did not really show any predictability. Actually, that is true that active fire is not really designed for the predictability. That is actually monitor ongoing fire events. So yeah, B is not really showing any underestimation. It's their purpose to monitor ongoing events. Just the point is that active fire or post-fire product, it cannot be used for predictions, surely, of course. And then C is weather index, and weather index sometimes, could predict fire events around here. However, other times did not really show any predictions in advance before ahead of fire events. And then C is fire radiative power. almost identical to active fire. Yeah, so did not really show predictability, although we expected to see radiant fire released from the vegetations. This is another data just for comparison. Before the fire events and ignition, canopy temperature, forest temperature has been, forest temperature increase over a large area, or around here. But active fire and D, okay, D is different. Active fire and B and C, active fire and radiative power did not really show any predictability in advance because they are designed to monitor ongoing fire. And D showed SMAP vegetation water contents. By theory, vegetation water content should be lower around the fire area. However, it's been it's the vegetation water contents was higher than adjacent area. Um, before the fire event, so seems to be poorly predicted. So this is just showing that heat amplifying forests. Before the fire event, we could see that forest temperature has increased already, which was correspond to the sensible heat. So it's not like that just temperature heat, there's a feedback and interaction between the canopy temperature and sensible heat, as we've seen in the very beginning of this presentation. Yeah, here there's a feedback between TC and HC here. There was a interactions between the fewer temperature and the sensible heat, so they increase and store lots of heat that makes forests vulnerable to fire spread. So this is basically showing that they can self-condition and intensify and spread destructive wildfires by storing heat in their vegetation fjords itself. So forest seems to have the power to intensify independently wildfires through these land surface and forest heat amplifying feedback, which increase sensible heat and from sensible heat from warmed canopies, and of course it will shut down evapotranspiration and stomata closer sometime under heat wave conditions, and further heating the forest again with elevated sensible heat. So once the sensible heat increased, there's further chain reactions to intensify the heating process. The fjords are drying up during this process, and temperature gradient and uneven distribution in heat can cause wind. We will look at this feedback with atmosphere later on in next session. So data show that fire spreads are very large. That's why the fire spread is very large in Canadian wildfires. Usually in Canadian wildfires, it turns out that they started in 3% of total burned areas, and then just remaining 97% are actually something that the initial ember is just spread into 90-70% of the total burned area. So because of this, planting more and more trees under heat wave conditions in dry soils is not really wise idea. And as we've seen in soil moisture sector, under dry soils, their efficiency of photosynthesis is tremendously decreased, right? So, but if you plant more and more trees in such soils, then they will not, of course, they will not do the job that we want, which would be carbon uptake, carbon sequestration. Only they will do is just burn more and more fires, because it will decrease fuel moisture and increase forest temperature and accelerating heat amplifying feedback. So we really have to be careful whether planting trees would be appropriate for the given forests and area. So to sum up, um, like for example, like SMAP, retrieval SMAP product, SMAP mission provide vegetation water contents from the empirical relationship with vegetation optical depths, which was traditionally estimated from vegetation index. However, nowadays they simultaneously retrieve it with soil moisture instead of without relying on vegetation index. However, still, when we looked at the vegetation obstacle depths, there were a very poor relationship with fire dynamics. And vegetation water contents, yeah, still, yeah, because that is rely on the NDVI climatology. It was just very static. Also, um, 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 there was another option for the forest temperature, yeah, which showed a very nice dynamic and with fire dynamics could see some interesting predictability ahead of combustion and flaming. However, they are available at low resolutions as compared to radar, SAR, infrared sensors. So it really depends on your needs, whether you are looking at the large scale heating process, or if you are looking at the high resolutions uh, pre-fire management, then it's better to look at like something like infrared sensors like eco stress data, or yeah, and so on. However, the SAR is, although SAR has higher resolutions, their signal is very difficult to analyze, very difficult to isolate soil moisture from their signal, because they are very sensitive to soil roughness and topography and some instrumental configurations like instance angle and so on. So high resolution does not always necessarily mean that it's better estimates. Okay, that's pretty much it. Okay, thank you very much for your attention. We will continue to talk about some more aspects of fire development in the next section. Thank you very much.